This is the second lecture on persistent homology. In this second lecture on persistent homology, we will first study the notion of filtration and then discuss an algorithm for computing the persistent homology. In the study of homology, we understood how it is a topological invariant and how it can help us distinguish between different spaces, different topological spaces. We saw how the use of algebra makes this a computationally amenable invariant, unlike, for example, homeomorphism, which was difficult to compute. Today, what we are going to see is how we can take this idea further and associate size measures on top of the homology groups. So in particular, we will understand how we can associate size measures with the homology groups of different dimension. So we are going to be talking about size of various cycles, the homology classes. In order to understand this for a simplicial complex K, let's assume that K is a simplicial complex that represents our topological space. So we will focus all attention on the simplicial complex. And for this lecture, again, we are going to study simplicial homology. So all the addition is with coefficients from Z2. Let's start with a simplicial complex K. In order to compute its homology and its persistent homology, we will begin by talking about how K is constructed from scratch. Now, imagine K is a building. You would like to construct it brick by brick. So you would first lay a brick, then apply some cement, which will help bind it with the next brick that you will include, and so on. So similarly, in order to build K, we need bricks. The bricks are our simplices, and we insert them one by one. So let's call each brick as sigma I. So the sigma sub I are included or added one by one in order to construct K. Now we order the simplices sigma sub I such that at any step of this construction process, we always have a K sub I, which is a simplicial complex. So this means that before including sigma sub I, all its faces should have already been included into K sub I minus 1. So this leads us to a sequence of simplicial complexes K sub I, beginning from the empty set, which is called K sub 0, and ending at K sub n, which is the simplicial complex K. All intermediate simplicial complexes are obtained from the previous one by the insertion of a single simplex. Remember, we have seen such a construction in the algorithm for computing Betti numbers. So in that algorithm, we have also seen that the simplices, when you insert them, they either create a cycle. So if sigma sub I is a K simplex, then it creates a K cycle, or it kills a K minus 1 cycle. So, so we want to associate a sign with each simplex, and we call a simplex as positive if it creates a cycle during its insertion, and we call it negative if it kills or destroys a cycle. Let's look at an example. The simplicial complex that we want to construct is shown here in the lower right box numbered 17. So K here is constructed in 17 steps, beginning with, well, actually here 0 already begins with the insertion of a vertex, but you may want to think of 0 as the empty set. So let's begin. So this is actually 18 steps, not 17. So we begin with insertion of a single vertex. Now we know that a single vertex creates a 0 cycle. So this is termed as positive, as is denoted here. And the simplex that is inserted is also written in the as a label for this box. The next vertex that is inserted is T, which also happens to be positive. In fact, all the vertices have to be positive simplices. Next, step 2, a third vertex U is inserted, which also happens to be positive. Step 3, you insert the edge ST. So now then you will notice that I think the way the boxes are set up, the box tells us what simplex is going to be inserted. So so this is step I minus 1, and you are inserting sigma I to give you k sub I. Right, so so I take my earlier comment back. Right, so here you start with k sub 0, and you are going to insert S in order to give you in the next step. So you insert the first simplex, sigma sub 1, to give you k sub 1. So in the third step, you insert the edge ST, and that gives you k sub 4. K sub 3, and so on. And you continue till you get the entire simplicial complex. So now let's go through this sequence in order to understand who is a positive simplex and who is a negative simplex. Now when you insert the edge ST, what you notice is that the insertion reduces the number of connected components by 1. So we will use the interpretation of the Betti numbers as the number of components, the number of 1 cycles, to immediately see whether a cycle is created or not. The insertion of ST reduces the number of components. So in this case, the Betti 0 reduces to 3. So hence the edge ST is called a negative simplex. So ST has a minus sign associated with it. So next you insert V, which is again positive, followed by the insertion of W, which is again positive. Next we insert SW, the edge SW. Now again, this insertion of this edge creates, it does not create a cycle, rather it destroys a zero cycle. So it reduces the number of connected components. So hence SW is negative. Next, we insert the edge TW. Now, if you look at the edge TW, when it's inserted, it creates a one cycle. So this is a creator, and hence TW is termed as a positive simplex. Next, the edge UV is negative. It reduces Betti sub 0. The edge SV is also negative. Next, the edge SU creates a cycle. It creates a one cycle, so hence it is positive. Next, the edge UW again is positive. It creates another cycle, a new cycle, hence it is positive. Followed by the edge TU, which again is positive. It creates yet another one cycle. So TU is positive. Now we move on to the insertion of the triangles. So first we insert the triangle TUW. Note that TUW could not have been inserted up until now because the edges TU, TW and UW were not inserted until the previous step. So now, so TUW can be inserted now, and so it is inserted, and when it is inserted, its boundary is one of the existing cycles, so which means that it kills that cycle TUW. When it is inserted, it destroys that cycle that was created actually in the previous step. So hence it is negative. TUW is negative. The triangle SUW is also negative because it also destroys a one cycle. The two simplex STU, the two simplex STU is also a negative simplex. It destroys a one cycle. And followed by the triangle SUV, that is shown in light pink, SUV, that is again negative because it destroys a one cycle. So by now, if you notice, for the quad STUW, for that all the four triangles have been inserted. So the triangle TUW is inserted, the triangle STW is not yet inserted, but then the other triangles SUW was inserted in step 14 and STU was also inserted in step 15. The fourth triangle of this tetrahedron STW is inserted in the last step. So this creates a two cycle. This creates a two cycle. So hence STW is called positive. Right? Now I would recommend that you pick any simplicial complex such as this, a simple one, and run through this exercise of classifying the simplices as positive or negative. So during these 17 steps, we have inserted multiple simplices, and we have also classified them as, at least manually, we have classified them as positive or negative. So this sequence of simplicial complexes that we get is called the filtration. In the So let's see some benefit of this filtration. In the incremental algorithm for computing Betti numbers, we already saw that during the process of computing the Betti numbers of a given simplicial complex K, we compute the Betti numbers of all simplicial complexes in the filtration. So what did we do there? We initialized Betti sub j to be 0. So here we are taking an example where the dimension of our simplicial complex K is 2. So all we need to do is initialize Betti sub 0, 1 and 2 to 0, and then we insert the simplices one by one into the filtration, or rather to form the filtration. And if sigma sub I is inserted in the ith step, let's say that little k is the dimension of sigma sub I. Sigma sub I could either lie in a k cycle, as in it forms a k cycle, because if it lies in a k cycle, in that case we increment the Betti sub k. We saw that this creates a new homology class, and hence the rank of that homology group, the kth homology group, increases by 1, and hence Betti k increases by 1. We saw that if this is not true, then the one of the homology clauses of the k minus 1 dimension is now destroyed, because the simplex sigma sub I forms the boundary of this of the corresponding k minus 1 cycle, and hence the rank of that homology group reduces by 1. So Betti sub k minus 1 is decremented. So remember that since the addition was using coefficients from Z2, the rank of the homology groups was easy to compute. Right, so this algorithm for computing Betti numbers was quite simple. Moving forward from the discussion from the previous lecture, we saw that the topological persistence was based on a lifetime analogy. Now, when we talk about the filtration, we again have a sequence of simplicial complexes, so we can again use this lifetime analogy in order to associate a lifetime with all the homology classes. The lifetime being the time of creation. So every cycle is labeled after its creator. There is a simplex that creates the cycle for a given filtration, and the cycle continues to live, or it persists till it is destroyed by the simplex, by the negative simplex that is inserted. So the cycle also has a destroyer, a negative simplex. The lifetime or the age of this cycle is called its persistence. Now, what does it mean to create a cycle? This is when, for example, when you have four edges already inserted, and when you insert the fifth, the 3 edges already inserted, and when you insert the 4th edge, then you create a cycle. So in this case, the edge E that you insert is called the creator, and after this insertion, so let's say you insert another edge E prime. E prime is also a creator of a second cycle. Now when you insert a triangle, this triangle actually destroys the one cycle that was created by E prime, and hence the age of this cycle, that was the one cycle that was created, is one, right? So one, namely the age of the cycle. So E prime was inserted, followed by E prime, followed by the triangle UVW. So the lifetime of the cycle that was created at E prime is 1, because it is destroyed in the next step. So this is what we mean by age of a cycle. So in this case, what we are measuring here is called index persistence, because the age is measured in terms of in units that comes from the index. So so the index, in the sense that so let's say E was the simplex sigma sub 3, and E prime is sigma sub 4, and UVW is sigma sub 5. The index is what is used to compute the age. Alternately, you can associate an actual age or a real value which is increasing to each of these simplices as they are inserted, and that difference can be used to compute persistence. This is what we did earlier for the case of Morse functions. So finally, we were pairing the creators and the destroyers. So in this particular example that I've shown here, we have a pair which is E prime and the triangle UVW. So we are pairing simplices now, right? So this is one of the pairs. So we want to now compute all such pairs that capture the lifetime of all cycles of all dimensions. So that is the goal of the persistent homology algorithm. We are going to see one approach towards the computation of topological persistence, which is called cycle search. This is very concrete in the sense it is easy to build the intuition for this algorithm, and after this algorithm we will also see how this leads to the more familiar matrix algorithm that we saw for homology computation. The cycle search algorithm maintains a data structure. Let's look at what data structure it maintains. This is essentially just a linear array, let's call it T, and it has n entries corresponding to the n simplices that you are going to insert. You can imagine, if you care about the implementation, that T behaves like a hash table. Initially, this array is empty, but once it's processed completely, what does it store? At the end, finally, it stores all the pairs of simplices. So specifically, after you process sigma sub j, right? So sigma sub j is the jth simplex that you're inserting. After you process this, if sigma sub j is negative, right, as in it destroys a cycle, then let's say it is paired with sigma sub I, right? So let's assume that we have found the pair sigma. When you insert sigma sub j, you know that it is paired with sigma sub I. Then T sub I, the ith entry, will contain j, right? So T sub I will contain j. And T sub I will also contain a so-called boundary list. This will be the list of all, this will be a list of positive simplices only. So this list will be a list of positive simplices, and this list will represent the cycle that was destroyed at sigma sub j. So this, so at I, you both store who it is paired with, namely j, and you also store a representation of the cycle that was destroyed when you insert sigma sub j, right? So we will use this data structure to understand the algorithm. So here is the cycle search algorithm. So let's see this step by step, and we will maintain the, remember, the data structure, and I would like to draw just a cartoon version of this data structure. So this is our T, and the ith entry is what we care about, and note that the ith entry also has a boundary list, right? That's like any other hash table. Okay. Now let's see what happens when you insert a negative simplex. Now the cycle search algorithm does essentially nothing when you encounter a positive simplex, because the positive simplex simply creates a cycle, so there is nothing to pair it with. The simplex that destroys the cycle comes later, so essentially you have to process all the negative simplices. So let's consider again that the same sigma j as the negative simplex, and I would like to use a concrete example to go through this exercise. So here we have a simplicial complex. This is a bit made up. So it has so it's again two-dimensional, so that it's easier to draw on the plane. So this is our k sub I at some, well, let me call it k sub L, right? So what we want to talk about now is a negative simplex sigma sub j, and I want to use a 2 simplex for sigma sub j. So the sigma sub j is a triangle, and I want to talk about the sigma sub j that kills the cycle created by the insertion of sigma sub I. So so let's say the long edge here is sigma sub I. The long edge here is sigma sub I, and let me give it a so in the interest of making this simple, I'm going to give this a number, so that I can write down successive numbers. So let me just label this as, so let's just count. So there's 3, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So this is, let's say, 18. My count may be wrong, but that's okay. So let's start with this edge. Let's call it 18. So let's say that's a sigma sub I, the edge sigma sub I was inserted as the last simplex for to obtain k sub L. We already see that sigma sub I is a positive simplex. It creates the cycle here, the cycle that looks like a pentagon. So this is a sigma sub I is a creator. Now let's say that following this we insert multiple edges and triangles, which are both creators and destroyers, right? So let's say that subsequent to this we insert another edge that I call 19, right? That is a creator, and then I insert a triangle that I call 20. So 20 is the triangle, let's remember that. And then I insert another edge that I call 21. And then I insert the triangle here, right? And that triangle is 22. The triangle is 20. And finally I insert a triangle which essentially destroys the cycle that was created at 18. And this triangle is 23. So our sigma sub j is 23. Now I want to find the pair for 23, and I want to find that it is 18, right? So the question is, how do I find it? So that's what we're going to do with the cycle search algorithm. So let's look at 23, and let me draw it here. I'll try to draw the key steps in this scratch space. So I have 23 here, sigma sub j. I know that it is negative because it does not create a cycle, so which means it kills a one cycle. And this is sigma sub j, right? So the way the algorithm starts is the first step. It creates a b sub 0. Let this be the ordered list of positive simplices in the boundary of sigma sub j, right? So what is the boundary of sigma sub j? It consists of 3 edges, right? It consists of 3 edges. I don't know the labels of all the 3 edges, but I know the label of 2 of them, so I'll just write those. Just the positive ones is enough, right? So I know 18 is positive because it created a cycle. So 18 is one of the positive simplices on the boundary of sigma j. Now how about the other edge? I think we called it 21. Now we saw that 21 was also a creator of a one cycle, so that is also positive. So b sub 0 initially has 18 and 21. The third edge here on the right, so that edge was present even before 18, and it did not create any cycle. Let's assume it did not create any cycle, so it is a negative edge, which means that it only destroyed a component, right? So we do not insert that particular edge. So which edge? Let's just put some labels so that is clear. The edge AC is negative, so I do not include that into b sub 0. So b sub 0 only has 21 and 18 for now, right? Okay. So what does this represent? So this is now representing the boundary. So I know that 23, the triangle 23 killed a cycle, and I want to somehow find the cycle that it killed, right? So I start with the current cycle that it killed. So the cycle that it killed is the boundary of the triangle sigma sub j that consists of 3 edges, and I look only at positive edges because those are the only potential pairs. So which is why I have 21 and 18 in the boundary, right? So so let's write that somewhere else. So I have b sub 0 has 18 and 21, right? And I want sigma sub y to represent the youngest simplex in b sub 0. Youngest means the ones that was inserted the last, so which means 21, right? So 21 is sigma sub y, the youngest. So naturally it is the y is the largest label, right? So largest label, hence 21. We go and look at the entry for y, right, in the array, right? If it were empty, right? If this entry were empty, then I have already found my pair, right? So I know y is sigma sub y is positive. I know sigma sub y is positive because I look only at positive simplices in b sub 0. And if t sub y is empty, then I know it is a creator and I have found the destroyer pair, right? So I set t sub y equal to j and I am done, right? But is that the case here? The edge 21 is a creator, but remember that during our sequence we found that 22 is a triangle that killed the cycle that was created by 21, right? So when you look at the entry corresponding to when you look at the entry corresponding to 21, this would already include 22, right? And it would already have a boundary list that will consist of some edges, right? So that is the edges corresponding to the cycle that 21 created, right? And that 22 destroyed. So this would already have a boundary list, right? And in fact that boundary list will include 21 and any other positive cycles, so which means another positive cycle, so it would actually have 21 and 19. 21 and 19 were the positive simplices that corresponded to the cycle, and that was destroyed when you insert 22, right? So going back to the algorithm, t of y is empty, then you have found your pair, but t of y here is not empty. In fact, it is occupied, right? So it is occupied, and this is what we call as a collision. So t of y is occupied, so we have a collision. Now what do? We have to expand our cycle to incorporate this collision, and the way we do that is by merging our existing b sub 0 with the boundary list that we have found at y, right? So this gives us our new b sub 1, and the way we merge is just by doing a simple addition, right? Again with coefficients from z2. What we find is that we have b sub 0 has 18 and 21, and the boundary list at y has 21 and 19. So when we merge, we get a boundary list which is 18, 19. 21 added plus another, the other 21 modulo 2 vanishes, right? So this gives us our new boundary list, which is B1, that consists of now 18 and 19. So what have we done here? We have started with a representation of the cycle. Initially it was 18 and initially it was 18 and then 18 and 21. So initially it was 18. I'm trying to draw with the same scratch space, 18 and 21. And we removed 21 and we expanded this by going back in time, right? We went back in time. That's what we did with the collision to find the that 21 was paired with 22, so when we merge the boundary list of 21 with B sub 0, we have a new representation of the cycle that existed at that particular moment, right? So this is what we have now, 18 and 19. And we again, so now we going back to the algorithm, we again find the youngest simplex in B sub 1. Now the youngest in B sub 1 is the one with the largest label, which is 19. Now you go back and look at 19 and see if it is occupied. Now you will notice that 19 also has to be occupied because if you look at our initial filtration at the bottom, you notice that the 19 was a creator and the cycle that it created was destroyed by 20, right? So you have yet another collision, so hence you have to merge B1 with the boundary list at 19. So the boundary list at 19 is paired with 20, right? And it has its own boundary list, right? That contains 19 and possibly one more of the edges. I'm guessing that the other two edges on the boundary of the triangle 20 are negative. So you will have only one entry, which is 19. And when you merge that list with B2, you get 18. So B2 is now 18. And we continue this process until we find an empty slot. So now what have we done here? We have again expanded by looking at the pair for 19, right? By looking at the pair for 19. And when we expanded, we found possibly another edge, or in this case, we said there is no edge, right? So now the representation of the cycle is only 18. Okay, so now we go into 18th entry, and of course 18th entry is empty, and we have found the pair, and we say that 18th pair is 23, and we store the boundary list here, 18. So this was a simple case where the boundary list consists of only one edge, but in many cases the boundary list can have multiple edges, right? Right. So that is the algorithm. So the reason it's called cycle search is hopefully clear now. You start with the representation of the cycle, which was b sub 0, and you go back in time and use the collisions to expand the search for this cycle until you find the creator cycle. Right. So the algorithm both computes the pair and a representation of the cycle that was created and destroyed. What about the runtime? So if p sub I is the persistence of sigma sub I, we know that this persistence is just j minus I. We are using index persistence here. We know that sigma sub I is found in pi steps. So because there are pi number of potential collisions. Of course, this is a conservative estimate. How much time does it take to resolve each collision? In order to find this, we look at this nesting property. So let's say that in the process of finding the creator, we have a collision. Let's say that the collision was at sigma sub g, right? So we are starting with j. In order to find I, and let's say we found a collision at g. So g is a positive, sigma sub g is a positive simplex, which has to be paired with sigma sub h. But we know that sigma sub h has to be has to have already been inserted. So h has to lie between g and j, this is the reason you actually have a collision. You know that g's pair is found, so h has to be between g and j. So the size of the boundary list cannot be more than pi, more than p sub I, right? So naturally the merge does not take more than p sub I time, right? So this is just a simple merge, so it doesn't take more than p sub I time. So even if you are conservative and say that the merge takes O of p sub I time, we know that sigma sub I can be found in n square time. This is again being conservative and saying that p sub I is O of n. So each collision takes O of n time for the merge, and we find sigma sub I in O of n steps, so totally O of n squared time. In order to find the pairs for all the simplices, the conservative estimate is O of n cubed. Right? So this cycle search algorithm has a running time of O of n cubed. Now this may seem like a very conservative estimate, but there is indeed some corner cases where the O of n cube time is actually achieved. There is a very nice 2-page paper. I think it's not a published paper. It's just it's available on the net by Morozov that you may want to look at. Okay, so let's wrap this up by going back to the group theoretic formulation. What did we essentially do here? We found creators of cycles and paired them with destroyers of these cycles. Now, in the formulation of the homology group, we saw that the homology group consists of homology classes. So these were all the cycles that were not bounding. So and hence they represented holes. So we formulated this as a quotient group. The quotient of the cycle group Z the quotient taken with the boundary group B, right, for the pth dimension. So now we can extend this notion of the homology group to incorporate the idea of persistence. And we have already done that. So let's formulate it now. The pth persistent homology group we can define for the dimension p as follows. So if you are given a pair ij where I is less than equal to j, the pth persistent homology groups for the pair ij can be recognized as all those cycles that were in ki, right, that remain cycles when you go up to k sub j, right? So now we take the quotient group, you take the quotient of z sub p of ki with b sub p of kj. So we take the quotient with b sub p of the simplicial complex at j, not at I anymore. Right? Now, since you take the quotient with this group, now b sub p at kj can have some elements that are not in z sub p. So we just to keep this well defined, we take the intersection with the cycles from k sub I, right, just to remove all the other newly inserted elements that do not play a role anyway, right? So we are taking the quotient, or looking at all the cycles in k sub I that remain cycles even in k sub j, right? And that's what the quotient here implies. So this is the definition of the pth persistent homology group. There is another way to look at this. So essentially, the pth persistent homology group for a pair ij are those homology classes of ki. So they are all those homology classes from ki, so which means all those that belong to the pth persistent, the pth homology group at I, that continue to exist in k sub j, right? And the way we can formulate this is by writing down an inclusion map. So there is an inclusion map that goes from the underlying space at ki to kj. Note that k sub j is obtained only by inserting new simplices. So there is a nice inclusion map from the underlying space of k sub I to underlying space of k sub j. This inclusion map induces a homomorphism, and that homomorphism is what we call as f sub p between I and j, right? So this homomorphism takes homology classes from h sub p at ki to h sub p at kj. The pth persistent homology group h sub p I comma j is simply the image of this homomorphism. It's simply the image of this homomorphism, right? And the rank of this pth persistent homology group is called the pth persistent Betti number. So we see how this idea of persistence as the lifetime of a cycle naturally fits in with the group theoretic formulation of homology. So in summary, we have seen an algorithm for computing pth persistent homology, essentially by pairing all the cycles. So when you pair all the simplices to represent all the cycles, you essentially have the pth persistent homology group for all ij. Now, the way the cycle search algorithm works, it started with the boundary representation of a particular simplex sigma sub j, and then went back in time and tried to find the creator. This can be formulated in using the boundary operator and the boundary matrix as well. And the collision essentially will be equivalent to column operations. And so you can rewrite the cycle search algorithm as a matrix algorithm using column operations. So this algorithm is also described in the book by Edelsbrunner and Harrer, and is also implemented in many softwares. And that algorithm is called the matrix algorithm for computing persistent homology. So I'm not going to talk about that algorithm in detail, but if you go through that description, you will find that this is exactly what it is doing. So we'll stop here with the discussion of an algorithm for computing topological persistence.